The counting circuit is a circuit that is built with the goal of creating a device that counts up to 10 on a 7-segment display. Because this circuit is so large, the project and this video have been split up into different sections. The first section of the circuit is, of course, the input. This is a simple push-button input that is wired low side. This implies that the circuit is high at rest and relies on a pull-up resistor. The components needed are the button and a resistor that is large enough to protect the 9-volt battery. This part of the circuit works to provide a reliable input to the rest of it. The next section of this circuit is the NAND gate oscillator. This is the most important section as it works as the motor of the circuit. This section uses two RCs, or resistance capacitance configurations, to create a clock signal. The first RC, RC1, is included as part of the circuit to extend the duration of the counting. This RC uses a large capacitor, anything above 10 microfarads is ideal, that charges up while the button on the input is being pressed. When it charges up, it still allows power to go to the rest of the circuit. Once the button is released, the capacitor expels the charge that it built up, continuing the stream of voltage passing on to the next section of the circuit. RC2, on the other hand, is responsible for actually creating the clock signal and setting its frequency. A clock signal is a constant and balanced rotation between high and low through time. Frequency is the measurement of the speed of a clock signal and is calculated like this, with the unit of measurement being hertz. This section of the circuit does this by having the capacitor feed back on itself through some resistors and a NAND gate that is emulating the functions of an inverter. The capacitor is able to create this oscillation because as it receives voltage and charges up, it also allows current to pass through it. This current gets inverted by the NAND gate, providing ground here. So, when the capacitor is fully charged, it expels all of its energy this way and can repeat the cycle forever. The next section of this circuit is the decade counter. This section is centered around the 4017 chip. This chip can take a clock signal at its input pin and move each pulse to a new pin until it gets to 10 when it resets. There are a few special pins on this chip. First, the reset pin. It can be used to reset the count to 0. It can be disabled if it is sent to ground, and it can be activated when provided power. For this circuit, it is not used, so it should be sent to ground. Second, the disable pin. This pin can be used to disable the counting and all of the output pins. It will stay disabled as long as the pin is provided power, but is sent to ground for the circuit because it is not being used. Finally, the divide by 10 or decade counter pin. It sends a positive output every 10 periods that is received at the input pin. This is the only output pin that is passed on to the other sections of this circuit. The function of this chip can be displayed using a 10 LED block because it shows the progression of the counting that the pin is doing. This next section focuses on another special functions chip. This is the 4516 and 4510 chips. The 4516 chip takes a clock pulse, which will now be the divided by 10 pulse coming out of the 4017 chip, and converts it to a binary number based on the amount of pulses that were detected before it. The 4516 does this function up to 16, while the 4510 does it up to 10. The 4510 is more applicable to the project because the final display is in Arabic numbers that are base 10. This chip has 4 output pins that will display the numbers that the pin wants them to in binary. The 4 output pins are also exactly what the next chip needs as its inputs. The next section focuses on the final special functions chip. This is the 4511. Its job is to decode binary numbers and prepare a series of outputs that lights up a 7-segment display. It has 4 input pins to take in binary numbers up to 9, and 7 output pins to match the 7 segments on a number display. This chip also has 3 special pins. This is the display test, blank input, and store pins. They can be wired like this so that they don't interfere with the proper function of this chip. Once this chip is properly wired, and it is connected to the 7-segment display by matching up the lettered pins, the circuit is complete. A PCB model inside of a case can then be built, as it looks better and it is more consistent.